Okay, today's topic is about the derivative and how to find the derivative using the limit definition from Calculus 1. My name is Kurt Overhiser, and I'll be your host as we walk through a couple of examples on how to use the definition of derivative. Okay, so it turns out that there are two definitions for the derivative. We're going to look at an example of each one. Okay, the first definition of derivative is going to be this one right here. It says f prime of a. The prime symbol means the derivative, and then that's going to be equal to the limit as x approaches a of your function f of x, and then from that you subtract f of a, and then the whole thing divided by x minus a. So you might remember from pre-calculus that this is called the difference quotient, and we're taking, in calculus what we do is we take the limit of the difference quotient in order to obtain the derivative. So this is definition 1. To look at an example on how to use this definition, we'll suppose that the function f of x is equal to the square root function, namely the square root of x. And we'll also assume that the letter a, which is a constant, is going to be given to us as the number 4. So we come back up to this definition and we start plugging some things in for the function and the value 4 for a, and we obtain this. The limit as x approaches 4 of f of x, which we know is the square root of x, minus f of a, which we know as the square root of 4, divided by x minus 4. And then we all know that the square root of 4 is equal to 2. So basically, our goal is to evaluate the limit as x approaches 4 of the square root of x minus square root of 4 we just said was 2 divided by x minus 4. So once we evaluate this limit, this will be equal to the derivative of the function at 4. So the question is how do we evaluate this limit? You can't just plug in 4 in for x, because if you do, you'll get division by 0. We know that in math that's not allowed. So we're going to have to, that x minus 4 that appears on the denominator is the problematic factor that we're going to have to get rid of. And the way we'll get rid of that is to use the idea of the conjugate, or the conjugate trick. The conjugate is where you switch the sign in the middle where the square root is. So like, for example, if you look at the numerator, the square root of x minus 2, its conjugate would be the square root of x plus 2. And then multiply the bottom by the same, because we're in essence multiplying by 1, so we don't want to change the value of anything. And then we go ahead and multiply out the top. And we get since x is positive, the square root of x times the square root of x would be x. And then you get plus 2 root x minus 2 root x, and then negative 2 times a positive 2 is a negative 4. So basically I just multiplied out the top, and the bottom I didn't multiply out. I didn't FOIL the bottom out because I just wanted to leave it in factored form, because I want to get rid of that x minus 4 on the bottom, since that's our problematic factor. And the nice thing about the conjugate is when you use FOIL, the outer and the inners will always cancel each other out. So you see that the positive 2 square root of x minus 2 square root of x cancels, and you just end up with x minus 4 on top. Okay, so we're at this stage where we canceled out the square roots of x, and now we're going to do another cancellation, but this time multiplicatively. We're going to multiplicatively cancel out the x minus 4s. One on top, one on the bottom. So cancel these out multiplicatively. It leaves us with 1 on the numerator, and then the square root of x plus 2 on the denominator. Next, we can use the direct substitution property in order to evaluate this limit, because now we can go ahead and plug the 4 into the bottom, and we will not get division by 0 here. So when we do that, we get 1 divided by the square root of 4 plus 2, and then that gives us 1 over 2 plus 2, which is equal to 1/4. So that is our answer right there. So what that means is if you were to make a graph of y equals the square root of x, a quick graph, it starts at the origin, it's a half of a parabola on its side, and it has a graph that looks like that. And if you go 1, 2, 3, 4 units out, so here's 4 right there. Here's the x and the y-axis. And what that says is that the slope at the slope of the curve at x equals 4 has a slope of 1/4, because that's what how we interpret the derivative geometrically is the slope. So there's the little tangent line that I drew, and that slope right there at that point is 1/4. So that's what basically we just found. There is a second definition that turns out to be equivalent to the definition that we just gave. This definition is, we'll call definition number 2. And this definition says that f prime of x, the derivative of f, is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And the example that we're going to look at to illustrate how this definition works is we'll use a parabola, and the equation for this parabola will be f of x equals x squared minus 5x. So if you look at the numerator of the difference quotient in this definition, it says f of x plus h minus f of x. So we already know what f of x is, because I'm giving it to you as x squared minus 5x. So the next step would be to figure out f of x plus h. And then what we do in order to do that, this kind of reminds you of composition of functions, where the original function is something squared minus 5 times that same something. That's what the x squared minus 5x means. So what we could do is we can put the idea of the something in parentheses and then square what's in the parentheses minus 5, and then put another set of parentheses next to the 5. What goes in the parentheses is usually x, but in this case we're going to put x plus h into both parentheses. Whatever you put into one parenthesis, you have to put in the same one into the other, because we're basically substituting x plus h in for x. So it used to be x squared, now it becomes x plus h squared. And then it used to be minus 5x, now it becomes minus 5 multiplied by the quantity x plus h. And then what we're going to do now is to multiply this out. We have to FOIL out the x plus h because it's being squared, distribute the minus 5, and in doing that we obtain x squared plus 2xh plus h squared. That's what we get when we FOIL out the x plus h squared. Now we have to distribute the minus 5, so it becomes minus 5x and then minus 5h. So now we can go ahead and use the definition and take the limit of this difference quotient. So we obtain f prime of x equals the limit as h approaches 0. F of x plus h, we just got through saying, turns out to be all that stuff that we multiplied out, x squared plus 2xh plus h squared minus 5x minus 5h. So this right here, this quantity represents f of x plus h. That's in this part, the first part of the limit definition. And then from that we need to subtract the function itself, which is x squared minus 5x. So this part represents f of x, and we're subtracting the two. So that's where our f of x plus h minus f of x comes from in the numerator in the limit definition. And then we're going to take this whole quantity and divide it by h. Okay, next it looks like we'll have to distribute that negative again, or the other negative. And when we distribute that negative, we'll see that some nice cancellations happen. So we'll put a negative x squared, and then here, because I'm distributing a negative with a negative 5x, a negative times a negative is positive 5x. That got rid of the parentheses, all divided by h. And so if we look carefully, we can see that the positive x squared and negative x squareds will cancel each other out. And then also a negative 5x and positive 5x. Those will cancel each other out additively. So that helps clean up the numerator a little bit. And what's left would be 2xh plus h squared minus 5h divided by h. And we take this limit as h approaches 0. But unfortunately you can't plug in h or 0 in for h quite yet, because we get division by 0. So to evaluate this limit, what we'll need to do is factor out an h on the numerator and then go ahead and cancel multiplicatively with the single h that you see in the denominator. So to this end, the h in the numerator, 2x plus h minus 5 divided by h. So I factor out the h on the top. Now the h on the top and the one h on the bottom will cancel multiplicatively, and then we'll be left with the limit as h approaches 0 of 2x plus h minus 5. And to evaluate this limit, all we need to do is to use the direct substitution property and plug in a 0 for h. So we get 2x plus 0, because that's what h is, or what h is approaching, and then minus 5. So we get as our final answer 2x minus 5. And this, of course, equals the derivative of the function that we are trying to find. So we started out with x squared minus 5x, and found, using this limiting process, we found that its derivative is 2x minus 5. And that's the example we're going to use for definition number 2. The advantage of this definition is it allows us to, instead of finding derivatives of functions at individual points, it allows us, you'll notice that the derivative itself is a function of x. So whatever x is in the original function, you take that same x, plug it into the derivative, which is a function of x, and you'll obtain the slope of the graph of your original function at that given point. So I guess we can, just kind of look here as an example. We could try f of 1. When we plug 1 in, we get 1 squared minus 5 times 1. And that's going to be equal to 1 minus 5, which equals negative 4. So when, in other words, we know that the point 1 comma negative 4 lies on the graph of our function. This is your x value, that's your y value, and then if we wanted to find the slope value, what we do is we take 1 and plug it into the derivative. The same number, x is 1, and we'll plug it into the derivative, we get 2 times 1 minus 5, and we get 2 minus 5, and that gives us a negative 3. So then the slope at x equals 1 on the graph of the original function, its tangent line is going to have a slope of negative 3. Okay, so this is basically f prime of 1. And you can pick whatever number you want for x. You can put 5 or 10 or 12 or fractions, and then if you take that same fraction and plug it into the derivative, you'll get the slope of the tangent line to the function at that point. Okay, so that concludes this topic of the limit definition of derivative, and hope this helped, and good luck in your studies. Bye-bye.